all going to be about whether we can actually do error correction in practice. It's one thing, and I've certainly done that myself for many years, to say, all right, let's build a simulation of a quantum computer, generate some errors, see if we can correct them. It's, as I hope you appreciate after today, entirely a different thing to say, here is a piece of hardware. Let's see if we can error correct this piece of hardware. And so after today, I hope you understand why that's hard, why it's different. And if it resonates with you, come talk to me and see if you can help me, because it's more than one person should be trying to do. So what do we have at the moment? In the fridge, we have 22 qubits, and they work quite well. We're still very much in the testing mode, but to first order, they seem to work as well as our previous chain of 9 qubits, which means these error rates, right? But this needs to be verified. The best bit when we went to this design is somehow magically in the process of changing it so you have a separate qubit chip and control chip, we got rid of our crosstalk, which was a wonderful 100 times bonus. So hardware, things are going well, but that makes my life hard, you know. When it comes to actually doing error correction, you've got to choose some kind of concrete error model. You can't just say, well, particularly for a topological code, which is what we're going to try to run on this hardware, let's just choose an arbitrary error rate. Because if the error rate is really high, the problem is really hard, and the likelihood that you're going to keep pace with your computer quickly reaches 0. So instead, what we're going to choose is some kind of level of error where we could say, we'd be happy. We will attempt to actually do useful applications at this level of error. So a few things to note are the speed of the gates that we're dealing with here. So you're looking at 40 nanosecond 2-qubit gates. The only thing that buys me a little bit of time is the fact we can't do CZ gates in parallel everywhere. So for example, if I'm doing a CZ gate here, then the 6 neighbors can't also be engaged in any CZ gate. So you can do them in parallel, but not neighboring in parallel. And what that does is it blows out your typical, 4-way nearest neighbor check. Instead of having 4 layers of CZ gates, you end up with 16. But as I said, in my case, that means I have of order 700 nanoseconds to do a round of error correction, as opposed to 160-ish. The other thing that we do have, which might help me a little bit, is that measurement and reset are slow. At the moment, they look like they won't be so slow that they slow things down any more than the limit set by the CZ gates, but they're slow. So we assume this set of parameters, which is not what we have now, but what we would need to do something useful, just so I can then see if I can write software to actually cope with that. So, well, what kind of software do we actually need here? If you really want to do the whole stack, well, you need something that takes an algorithm and then kind of maps it down to a 2D array of hardware. Now, I'm not specifically saying that we're going to do precisely the surface code, but it's something that involves a 2D nearest neighbor array of qubits, local checks, local manipulations. I'll put one more layer of restriction on that in a sec. And I'd like to be able to divide these layers, so take my algorithm and create layers where we're either measuring stabilizers, transforming stabilizers. So this is a fragment of doing a logical Hadamard gate. So we transversely do the Hadamard here, and then there's actually an offset operation where we literally take our qubits and just swap twice so that we do a diagonal move. So to the best of my knowledge, this covers everything you could ever want to do in this type of hardware. Maybe it doesn't, but it gives me enough generality to do what I want to do. So just in the interest of giving a larger view of what this means, here is an example of a Toffoli gate with state distillation, two rounds of state distillation, the standard 15-to-1 state distillation. So what I'm saying is you would want software that obviously takes rather a lot more than just a single Toffoli gate, breaks it down into the gates that correspond to the actual Toffoli gate. That's this thin slice in the middle here. And the necessary state distillations, each one of these big fancy boxes is an A-state distillation. So this in here is a single A-state distillation. You see there are 8 of them here, which is one more than you need for redundancy for the 7 T gates that are actually in the Toffoli gate. And then there's a Y-state distillation here, which gets copied with a bunch of C-knots and Hadamides. So at the moment, this point in time in history, something like this is built by hand in SketchUp, right? Clearly that's not going to fly. We need a big piece of automated software that lays it all out in 3D and then slices it up into some small number of unique tiles that you can imagine sending to your hardware. Okay, execute this tile, execute that tile. And not just that, it has to take the corrected measurement string back from your computer and say, well, certain things that are done dynamically. You'll notice there are no connections between the state distillation and the actual skeleton in the middle of this Toffoli gate, because until you know which ones of those succeeded and where the actual corrections are required, for example, all of the Y states on the left, they are only used if the T gate returns the value you don't want, all right? So there's interactive measurement in here that determines which one of these, or if you even need one of these to connect. So that has to be done on the fly. So you need software, cuts all into tiles, software that takes the corrected measurements and then farms out the right tiles at the right time to the right places. And I'll confess that this is, right now, not my problem. I mean, I can only do so much, and that's not what we're focused on today. Instead, since I only have 2 hands, we sit with just starting with memory, all right? Let's keep it simple. So there'll be no interactive, given a whole set of corrected measurements, let's work out which tile to go next. It's all going to be fixed beforehand. We know what sequence of tiles we want. The tiles will be so simple I can work them out by hand. And really, all of the focus is on the following. Do a simulation, generate a whole bunch of uncorrected measurements, and do that offline. Writing a simulator that runs anywhere near as fast as the actual quantum computer, I think, is probably not possible. And it's not necessary anyway. So just pre-simulate all the measurements, particularly in this case where it's not interactive. And then really ask yourself the question, given a known sequence of tiles, and this question mark means you don't really feed these tiles, which are layers of gates, into this. We'll talk about that in detail, what you really want to feed in. A transformation of this to make it faster, and a whole bunch of uncorrected measurements. Can you turn that information into a stream of corrected measurements as quickly as the computer would run at the target error rate that we mentioned at the beginning? To do that, we're going to need to build tiles out of really 2 types of circuits for our hardware. So one type is a standard stabilizer measurement. We're only going to have one type of stabilizer measurement, which is this one. Basically, we can measure Z stabilizers. So this is a standard measure of Z stabilizer on whatever I interact with, measurement ancilla. And then when we want to measure the other type, well, we just Hadamard the data qubits. And so we're just doing layers of 2 classes of Z stabilizer measurements. We also need to be able to remove leakage from our system. So we don't really have qubits. We have multi-level systems. They can leak to higher states. That has to be part of the hardware level coping mechanism. And so you can prepare a fresh ancilla. And this just copies in a manner appropriate for our hardware the information without moving the 2-state, reset the old qubit, and you end up with a clean object if everything goes well. We are still in the process of testing reset, but something like that has to work. That's our best guess is what will work at the moment. So when you go and lay that out, you end up with a great big mess. So to help cope with that mess, here's a little bit of a key, and I'll show a little bit of an animation about what's really going on in here. The main thing to remember is sort of stoplight. Green means initialize, amber is transform. These are all obviously CZ gates, and then red for stop is measure, okay? So let's have a look at what that means for us. So you initialize a bunch of your ancilla qubits, Hadamard transform them, and then you start interacting, north, west, east, south. one set of them. And as I mentioned here, my goal here is to really emphasize the parallelism restrictions we have. So it's only one small part of the stabilizers you measure first. And then you go to the next class, and then the third class, and then finally the fourth class of stabilizer measurement. And you want to do that a few times. We have not talked about leakage yet, so let's just let that run a bit more. And then once you've done a few rounds of that, you want to do a leakage removal circuit, which is here. So what we've got here is reset a neighboring ancilla qubit, move your data to it, so you can see that over here. Reset an ancilla, move your data to it, and then reset where you started. So obviously, when you actually do this in hardware, there's not these huge voids. They're just there for visualization purposes. But I hope that gives you the feel of the lack of parallelism in our system and the time scale of what it all occurs over. So explicitly in numbers, you end up with an approximately 720 nanosecond cycle. So you have to cope with about 1.4 million cycles a second. I'm sort of debating as to whether it's better to be in presentation mode or not, because you have to keep cycling through the slides, but we'll see which works best. Okay, so we have our tiles. We have two different measurement tiles and an offset tile. Ultimately, when you remove leakage, that's all you're doing. You're just really shifting the qubits over one. Then we want to do some kind of analysis on this. You can't feed all of these billions of gates into a processor and expect it to do anything in real time. It's got to all be pre-computed. And this is something we've been talking about for many years. So for most people, this won't be anything new. You look at each of your gates, every possible error, work out where they will be detected. The one thing that we do require to be able to handle a scheme of this kind, and again, I'm not specifically restricting myself to square surface codes. We want something that will be able to handle more complicated lattice surgery and triangular surface codes. The one thing I want is that if you have an error that generates more than 2 detection events, for example, this guy, it should decompose into errors that generate no more than 2. So let's just go back a slide and think about what that means. If, for example, I have a YY error, it means it's going to generate this pair of detection events. This is the ZZ pair, and this pair of detection events, the XX pair. So you generate a YY error in software, you get 4 detection events. It's got to be possible to find 2 other errors on the same gate that add up to the same process, okay? If you can do that, then you can use minimum weight perfect matching. And you might ask, well, why do you care about minimum weight perfect matching? It's all about speed. What algorithm do you expect can possibly keep pace with the hardware? At the moment, I can't see anything other than minimum weight perfect matching keeping pace. And even for that, we'll see it's very, very hard to make that happen. And we can't do it yet. So let's say we have this condition, so we can decompose all of our more complicated detection patterns into simpler detection patterns. What you can do is turn that around. So for every gate, we've done this analysis. And so instead of saying, well, we have a gate, a bunch of errors and lines, what you can instead do is say, well, let's focus on the lines instead. And for each one of these lines, create a list of errors that leads to it. And even more than that, if you have a think about these pairs of this pair of diagrams. So these are all the pairs of detection events that can arise from all errors on one single gate. So if you think one of these lines is present, you know there's been an error on this gate. You also know that there's an increased chance, if there is an error on this gate, that there's also an error of the opposite type. Okay? Just goes without saying that if there's a few Z errors that led to this, there could be a few X errors that led to one of these. So what you can also do in addition is say, well, if I have this, I should also remember these 3 lines, because if I believe I've got one of these, I should mark all of these as more likely. It's just extra information you can use. So that's what you do. You sort of invert this structure to focus on the lines, the list of errors that lead to each line. You can add them all up so you have the total probability of that line, and you also get a full list of all the lines that become suspicious. You can even work out their probability of being suspicious if you have a belief that you have one of these lines. Okay, and then you want to make it smaller. So why would you want to make it smaller? I mean, this is not the first time we've written a minimum weight perfect matching algorithm for a 2D array of qubits. Just our previous version was not fast enough by a factor of several hundred. All right, so we need a faster version. So everything about this talk is how do you make it run as fast as I can make it run, right? Not as fast as humanly possible. I'm really, really hoping there are some humans in the room that can make it run faster than I can, but as fast as I can make it run. So one of the first things you want to do if you want anything to run fast is not use too much memory. No dynamic memory allocation. You're dead in the water as soon as you do any of that. And as much as possible, get everything to fit into cache, use everything, reuse everything, you know, really make everything light data. So one way you can do that is compress the data structures. So when you first do this analysis, as you can imagine, there are a lot of different type of lines, about 3,500 just for simple memory, okay? So lots of different lines. And of course, it would be a lot more than that if you went to computation, which is not great news. So you want to go through and compress it, and there are a bunch of things that we do to make that happen. If the lines point in the same direction and they share an error, and all of their suspicious lines are the same, then you can combine them. They don't need to be distinct, and you can throw away any of the errors that are not shared. And you can do that for a while, and then eventually you have to start saying, well, we have 2 lines, they have different total property, they go in the same direction, but their suspicious lines don't agree, so let's just throw away all the suspicious lines, so we won't use that extra information in the algorithm, and just combine them until you have no more than 256, which is a single byte of information. What that allows you to do is look at each point in this space and create a small list of bytes, each one of which represents a line. So it's just a very light data structure to say, oh, I have all these directions if I'm looking from here. That's what my universe looks like. So another thing you can do is really compress down what the line is. I mean, the line nominally is a vector, and that's normally not 4 bytes. So instead what you do is you make your little universe a finite size. As soon as you do that, it means you can get from anywhere to anywhere just by adding an integer. And so you use 2 bytes of this just for a little integer that gets you from anywhere to anywhere. It also makes the code run quicker. You don't have 3 coordinates that you need to add, and so on and so forth. So when you're done, you end up with a number of slices that you can use to reconstruct your space, about 10. We're going for order 100 qubits that we are going to handle with a single core. And you know, it's really small, about 11 kilobytes, 11, 12 kilobytes is enough to represent all the information we care about that we can derive from our tiles and our error model. So let's just have a look at what that looks like. So again, I'm going to flick back and forth between these. No, that one. This one. So the point here is that you set a small area of your computer to store just 32 bytes of information, right? So a column of 32 bytes of information allows you then to capture all of this structure, because the tiles themselves, 11 kilobytes of information, are in cache, and all I need to do is say, oh, well, I want tile 5 here. And so the top part of this structure is then just a single byte of information. This top one is 5. And then time passes, we reset it, we get our new layer of measurement information. You can see some little red dots. They're our detection events from our hardware. And essentially, all you need to do to make this happen is update a single byte in cache to say this layer represents that tile, and you get all of your measurements as a bit array, and you have to do a few bit manipulations of them, and then share those bit results across the data structure that represents this small universe. So we typically go, a 16 by 16 array of points by 32. And inside that, we store information such as there is or is not a detection event here, and a few other things totaling about 8 bytes of information, well, totaling exactly 8 bytes of information, that will allow us to run minimum weight perfect matching, as we will see. So again, the emphasis here is as close to zero possible processing as you can. So here we have byte update and bit field manipulations to get to this point in the algorithm, the point where you can start solving things. All right, next. So we have our problem now, right? Our problem is in our computer. Now we need to start solving it. So how do we do that? As I said, I like minimum weight perfect matching a lot, probably because it's what I've been doing for entirely too long, but it also seems, as I hope I can argue today, the right way to try to keep pace with this type of hardware. Of course, if you're working on neutral atoms, you were done a long time ago. You didn't need to worry about this talk at all. But for superconducting qubits at their current speed and future speeds, which is supposedly even going to be quicker, so my colleagues tell me, you really, really, really need to worry about whether your decoder is fast. So what we want to do now is go through minimum weight perfect matching in a little bit of detail as it currently stands. Minimum weight perfect matching is more an algorithm framework. If you ever go and look it up, you will find a series of very vague steps that you then need to go and implement in some manner. So it's not your typical textbook algorithm where it's really all spelt out. You then need to go and do research as to what is the best way to implement those steps for your problem. And so this is an example of what that means for topological quantum error correction. And first, we just need a few definitions. So they're all basic graph definitions, nothing crazy. So this is a matched graph with boundaries. I hope that's completely intuitive. We have vertices, edges, boundaries. We have edges that can either be unmatched or matched, and vertices that either can be matched or unmatched. Very simple. Here's a cycle. Again, I just want to make sure that this is all clear, what we're talking about. And one more thing, we need an alternating tree. So it's a tree, which means a graph with no cycles. Here is a graph with no cycles. Perhaps not quite standard, it's allowed to end in a boundary. It consists of alternating unmatched and matched edges, and that's all. So it's a definition which we need to really talk about the algorithm. Just let that absorb for a little bit. So what are we going to do? So when you focus on minimum weight perfect matching for topological quantum error correction, you can cast the algorithm in the following manner, and only for this problem, okay? You can choose a vertex. You can explore, which, if you remember that big water pipe, remember, it's right here, water pipe structure. It's like pouring water into the vertex so it kind of bleeds along these pipes. A fatter pipe lets water go quicker, a thinner restricts it. So that's what you do in code. You pour water into the vertex that bleed along the pipes until you hit something of interest. So something of interest could be another vertex or a boundary. And if that thing of interest is unmatched, so in this case, the vertex is unmatched, and a boundary is always unmatched, you can match with it. So in this case, just for the hell of it, I chose to match with boundaries. So that's one class of thing that can happen when you run the algorithm. Another class of thing that can happen is you choose a vertex, you start exploring, but then you hit another exploratory region. You connect up with something that's already matched, and you have to form an alternating tree. So here is an alternating tree. Here's the root, the unmatched, the matched edge. Once you do that, if you find that the alternating tree has a leaf, so that's the end of the tree, that is unmatched, you can augment the path from the leaf to the root, which means take this path from the leaf to the root and change every matched edge into unmatched and every unmatched into matched. And as you can see, that will help you here. You'll end up with one fewer unmatched vertices. And that's always going to be the case. The root becomes matched, and nothing else becomes unmatched. So that's the next class of problem. More than that, well, you can have things like, well, this was already done. We choose this one and explore, collide, form our alternating tree, but we're still not done. The alternating tree doesn't touch anything that's unmatched. So what you do is you continue to pour water in here and make that push this water smaller. And when that happens, you get this kind of push me, pull me effect. This gets bigger, this gets smaller, this gets bigger. That's what you see down there here, the extreme of that. This has grown to full size, this has shrunk to nothing. This has grown to full size, and fortunately has connected with something else of interest, an unmatched vertex. We now have an alternating path from root to leaf, and you augment that. You match your vertices. There are more cases. Here's another one. We want to match this with something. So we start pouring water in it. That's going to make this one shrink and this one grow. And I promise there's a finite number of cases, just one more slide, so bear with me here, okay? This is not the next 20 minutes, just two more. So this one gets bigger, this one smaller, this one bigger, and then they collide. And what we have now is an inability to put any more water in here, because if this gets bigger, this one's trying to get bigger too. So now you get a cycle. That cycle gets packaged into a new structure called a blossom. It gets effectively treated like a single vertex from now on. And so now you start pouring water into the entire structure as a whole. So you end up with this complicated flower-like, that's why it's called a blossom, growth. And you keep doing that until it collides with something of interest, here a boundary, and you have, again, an alternating path to the root. You augment it, you're done. Last slide, promise. Well, last slide on the algorithm. So now you already have a blossom. You're going to start here, expand until the blossom water goes to 0. That's what's happened here. We've squeezed all the blossom water away. And we need to keep expanding. To do that, we need to expand the blossom. We've got to break it apart. All right, once you do that, you have a nice chain of vertices. You can keep expanding, contracting, expanding, contracting, expanding until you hit something of interest and you augment back to the path. So in more formal terms, you have these operations, and that completely characterizes the algorithm. So, you can either increase, decrease an alternating tree, that's one, add a matched pair to an alternating tree, create a blossom, expand a blossom, or augment a path from leaf to root. Those are the only operations you need to do in matching. The complexities are numerous when you try to do this. Things like blossoms contain blossoms of blossoms, and you've got to write code that copes with that. It's got to be fast. You have to do annoying things like, all right, so you can easily imagine how you would do a breadth-first search for this part of the algorithm, the inner part. It's not so easy to do this kind of uniform breadth-first search around, but that's still possible. But worse than that, you have to remember enough information in the center of this. See how there's a little gap here? So that when you run it in reverse, you've got to be able to do it in reverse as well, this little hole in 3D reappears at the right time. So it's a pain to implement. It's very complicated to even get it to work. Yep. But, again, you keep the data light, so we've got this small universe. You never, at the error rate we've chosen to focus on, get more than 256 vertices, so you can keep a small finite number of them in memory, recycle them, small finite number of blossoms, and again, keep everything static memory reused. So, is all of this good enough? So basically we've explained how the algorithm works. Now we want to show you how it works. So let's have a look. So time begins, the computer sends a tile to the hardware, generates some measurements, and the checks pass. You'll see there are no red dots. Send another tile, generate measurements. Some of the checks indicate the presence of errors. And so we go and choose one of those detection events to focus on. We're going to try to fix things. We're going to try to match that with something. The first thing that happens is we go and request more measurement data because there's nothing in the future. We can't explore uniformly in all directions if we don't know what comes next. There's nothing in the future. We've got to go and get it. So we go get that. And then we're going to have a look in every direction around this detection event to see how much water can I safely put in. All right? We found another detection event. Great. We want to also look around that to see how much water we can put there. To do that, we need more measurement data, so we go get that. And again, we look around it, see how much is safe, go back to looking around this guy till we know how much is safe. And then once we know how much water is safe to put around both, we choose to put an equal amount of water around both so that they just touch and match them, okay? You choose that just because it takes up a smaller volume of space-time. It's more likely that you will avoid future collisions when you try to match other detection events if you keep two small spheres rather than one big sphere. It's just lower volume. And then we do that again and again and again, okay? The point of this animation is not to provide eye candy, right? The point is to really give you a feel for the complexity of this algorithm and its absolute computational cost. Most of the time, 85% of the time, what the algorithm does is really greedy. You look for neighboring detection events and you match them, all right? So 85% of the time, that's what you do. And then you might be sitting there thinking, yeah, but the other 15% must be a nightmare. And well, yeah, it's bad, but this is what's happening here. This is one of the other bad 15% of the time. You can see that, you know, the structure had to go further, but we didn't sit there for 10 minutes. So what you find when you do this is that 85% of the time you're doing a greedy algorithm, and that takes half of your time. And the other 15% of the time you're doing more complicated things, and that takes another half of the time. So, you know, you can, in your own mind, work out what that really means. Even in the hard cases, some are harder than other. But the point is that even if the hard cases became free, things would only get twice as fast and be reduced to something that looks entirely like a local greedy algorithm. So, at least in my mind, I find it very hard to imagine how you can write any algorithm that's going to run faster. It's local. The runtime grows as the number of detection events. If there's no detection events, there's nothing to do. The lower the error rate is, the easier everything gets, the more often you're doing these easy cases. Even at a 10 to the minus 3 2-qubit gate target, you really don't have that many hard cases, and they're not really that expensive. So the question, I guess, then is, you know, well, great. Here's a cache-optimized, local, most of the time doing greedy algorithm. Is that good enough? And the answer is no. So I've spent about 18 months on this, which is kind of embarrassing. But, you know, when you wanted something to run fast, it takes a long time to write, and sometimes you'll try something, and a few months later you go, you know what, that didn't actually help. You go back and you try something different, and you go around and look at the profiler, and it takes a lot of time, and it can get very depressing, honestly. It's very hard work, okay? You know what needs to happen. It's not like you're going to discover anything new scientifically. You've just got to get it really, really fast. So the current runtime looks tantalizingly close at first glance. So it takes 1.16 seconds to do what was supposed to take 1 second at first glance. So it's 90 qubits, 1.4 million rounds. It's 3 million detection events. So on the one hand, that makes me happy, but what makes me sad is the following. A big computer is not going to be just 100 qubits, right? It might be 1 million qubits. So it's got to be made parallel. When you want to make it parallel, the ideal way of doing that, and there's apparently an image here which cannot be displayed, so I am going to actually pull that image up because it's good for discussion purposes. When you actually want to do that, ideally, you would like to be able to cluster your detection events into provably separate areas. So here is that missing image which didn't load for some reason. So here's an example of a way you can provably separate errors. If this is true, if you have detection events that a cluster is defined to be a group of detection events where if you draw a sphere centered at every detection event with radius, the radius of the cluster, so the furthest away other detection event, and all of those spheres don't touch any other spheres outside the cluster, then you can prove that you never need to consider anything else anywhere nearby. And also because we're dealing with topological quantum error correction and detection events are clustered, you can prove that the chance of a growing size cluster dies off exponentially. So this is what you want. This algorithm is not the best algorithm. I hope to get a better one. If you can think of a better way of breaking this up so that you don't have this kind of effect, you know, all of this empty space that has to be empty so that I mean, in practice, when you actually match these things, what are you going to really get? You're going to get a small sphere here, small sphere here, small sphere here, small sphere here, and you'll be done. So it's not really true that you would need all this free, but I don't know a better way of checking. So you have to parallelize. In my ideal world, that would be done as follows. You put all of the measurement results of, say, this square, so this is, say, of order 900 qubits, into each core. So this central core takes all of this one takes all of this 900 qubits, convert it all into detection events, break it down into clusters, and then based on, say, some simple rules such as you order the detection events such that the ones closest to this direction are priorities, if that one is in your square, you match it. So for example, this one, this cluster, would belong to this processor, for example. And this would be a perfectly acceptable way of parallelizing if you could get the code to run fast enough. But. At the moment, about 10% of the time is spent just generating the detection events. Okay? You might say, that seems unreasonable. Why on earth does it take so much time? But if you imagine in your mind's eye the 900 qubits here, so that's 900 bits of information on measurements. 1.4 million of those a second. So this is well over 1 billion bits of information you have to process. You have to take these billion bits and compare them with some other billion bits. Then you have to iterate over those billion bits and throw out where there are ones, the detection events in another data structure. You can pretty clearly see you've already spent all of the resources of a standard core. You're done. Even at 3.5 gigahertz, top of the line processing core, you're done. You can't do it. And you might say, well, that's probably not such a big issue. That sounds exactly like something that you can do in an FPGA much more effectively, and that's probably true. So that's maybe not the biggest issue. But you then also want to divide things into clusters. And if you think back to what that meant, it meant doing this kind of breadth-first search around each one of those. That operation would be more expensive than minimum weight perfect matching that usually only had to do very, very small breadth-first searches. Okay? So what on earth is going to do that? I've asked people whether you can do a breadth-first search in an FPGA. The answer so far has been no. If you know how to do that, let me know. Or can think of some other algorithm. Let me just go back to this one. So it's a very concrete question. If you can think of a way to do this, cluster the detection events in an FPGA. It does not have to be by putting spheres around each one, but some way to provably separate them so that you can then farm them out to the appropriate core, that'd be great. Because this is clearly, if you think about how expensive the matching was and the fact that this is more searching and more expensive, too expensive to be done on a core. Other things, well, I hadn't done any actual Pauli frame updating yet. So it was just the matching that I focused on. And again, that's very FPGA appropriate, so perhaps that's not your biggest concern. But what we didn't do is any use of all that, here is a line, here are a bunch of suspicious lines. There was no way enough time. That sort of doubles your processing time again. We just couldn't do it. And we didn't do any handling of broken qubits. When you start doing that, you get larger circuits that are moving around these big holes, and you end up with lines that go through multiple layers, and it all just gets much more complicated, right? And more complicated equals slower, so we didn't do that either. So to a good approximation, you probably have to not have this feature in your code, not have this feature in your code either. As best as possible, get this into the FPGA, and if you really can, you want to get some form of clustering into the FPGA, which I don't know how to do. So the other option, which would be sort of a worst case embarrassing situation for us theorists, would be you would have to concede that there is a threshold that has nothing to do with your error correction code, nothing to do with the hardware, it's to do with your decoder. Your decoder can literally not keep pace with the hardware unless the error rate is low enough. So I mean, this problem would get a whole lot easier if the error rate was 10 to the minus 4, not 10 to the minus 3. And then everything would work and you'd be fine. But if you spend 3 years in a superconducting qubit lab, you get the feeling that that's probably not happening, okay? You really in any hardware. It's very, very hard to achieve. It's not something you can rely on. So we need to try very hard to get this to work close to the 10 to the minus 3, which is already borderline to get to. All right, so I hope that's some food for thought. Thanks for your attention.
All right, thank you, Austin. Let's take some questions. Let's start with someone who hasn't had.
So to talk about this reset gate a little bit, do I have to understand the action of the Gmon C phase outside of the qubit subspace in order to get why this gate works, or is there some simple explanation?
You basically interact dissipatively with a resonator. You bias it in such a way that it relaxes quickly. So it turns out that with our qubits, it's still in progress. You can get a tunable relaxation rate. And we hope that we can tune it to be about 15 nanoseconds, and then in 100 nanoseconds, it's reset to, say, 10 to the minus 3. There's still hopes, but it seems like it's what we're working on. We'll see if it works out. Yeah.
Hey, so not to put too fine a point on this, but you work for Google.
Yeah.
So why are you asking us for help optimizing your code?
See, it's a good question, and the answer is because I've certainly tried to talk to specialist programmers, but you've got to get over that barrier of entry. We're talking about topological quantum error correction. So it's not trivial to break this down in a way where you give them the freedom to optimize without constantly telling them, you can't do that. No, you can't do that because that's not going to work for my error correction. So, you know, maybe that's just a limitation on me, but, you know, I've had PhD students from computer science where I try to train them up and spent years with them trying to get them to the stage where this is something they can help me with. It hasn't worked. I've worked with people at Google over extended periods of time and tried to get them even into minimum weight perfect matching. Minimum weight perfect matching is not that simple. And so I've had people that said, yes, we can do anything, choke and die, when it just comes to doing minimum weight perfect matching. So, you know, have a think about what Google mostly does. Mostly it's not high-end programming. It's very large-scale, robust, customer-focused programming. Not to take anything away from that. I can't do that either, right? But it's different. So it's a skills gap. How do you get someone that is super good at writing really, really fast code and not put up learning enough about quantum computing and this algorithm to actually spend probably a whole year of their life helping you? Yeah. Maybe there's a better way of thinking. I've tried and failed. Yeah.
Thanks, Elston. I'm very sympathetic to the goal of trying to get a fast decoding algorithm, and I can see that part of your problem is you're saying that your hardware runs very, very fast.
Yeah.
But I'm just curious, is there any scope for actually just running it at a slower clock speed, which might initially sound like a daft thing, but if the C0 error rate is much, much worse than like the decoherence time over the time that it takes to run something on one clock cycle, then you can actually get longer survival times by running at lower clock speeds?
The issue is at this point in time in history, it's not an option. At this point in time, No quantum computing hardware in the world works. Nothing is good enough to actually run error correction. So we have to get our error rate down, and one of the ways we get our error rate down is we run faster, okay? So at the moment, it's not a valid technique to make things run slower, because that would make the error rates higher, and we would be even further away from even running error correction at all. Right? If our error rates were really low, yeah, well, we're decoherence limited. These are superconducting qubits. We're decoherence limited. We can't run slower. Not at the moment.
Just because the blocks, of course, remind me of renormalization decoders,
Yeah.
do you think we have to move to a renormalization group?
I
Take a
don't
hit
know
in the
whether that
threshold?
solves these problems. I guess you'd need to do the analysis and see whether it really works out to be a cheaper decoding algorithm.
It seems maybe nicer in terms of mapping onto an FPGA with propagation between the blocks.
Maybe.
Maybe.
But, you know, an FPGA is not infinite size. I don't know the answer to that. Maybe. It'd be great if someone looked into it.
Yeah, to follow that, I mean, we explored the Harrington decoder exactly for this problem, that we worry that it's too slow. And the Harrington decoder is very simple. It's just a cellular automaton, it's local memory, and it's an update rule. But of course, you need a hardware that then, well, the point is it has a bad threshold.
Yeah.
And the second thing is you need a hardware that exactly implements it at this cellular automaton level, with just the NOT gate, you know, with the transistors that you need, and not as some, you know, some pre-made hardware.
Yeah. I mean, in my experience, a lot of these simple decoders, when you really look at their guts, they're not that simple because they involve explorations over larger areas. And when you start doing that exploration, that's really expensive. So renormalizing group, you're grouping a cluster of detection events here that then needs to find a cluster over here, and it actually is not obvious that it's faster. Maybe it can be. It would be good to look into. I don't know. But yeah, the other issue is you pay for code distance. It's not an optimal decoder. It doesn't get the full code distance. And I'm unwilling to make that trade-off at the moment. People work so hard to make qubits. I'm unwilling to tell them, oh, you have to make 4 times or 8 times as many qubits. Sorry.
All right, we'll take a 15-minute break now and resume after. Thank you, Austin.